ATLaS addresses a fundamental challenge in LLM agent tuning. Traditional methods use supervised fine-tuning on complete expert trajectories, but this approach can lead to overfitting and poor generalization to new scenarios. ATLaS takes a different approach by identifying only the critical steps that are essential for success. By focusing training on just these steps, about 30% of trajectories, ATLaS achieves better performance while reducing computational costs and avoiding expert bias that can limit an agent's ability to generalize to novel states. Figure 1 provides a visual overview of how ATLaS works. The process begins with collecting expert trajectories from diverse interactive environments. Instead of training on every step, ATLaS identifies only the critical steps, shown in yellow, that are essential to task success. The paper shows that by training on just 30% of the most important steps, the model not only reduces training costs, but actually achieves better performance. This counterintuitive less is better approach works because it reduces overfitting to specific expert behaviors while capturing the crucial decision points. Speaker notes. The methodology section explains how ATLaS defines and selects critical steps. These are categorized into 4 types: plan creation, formulating subgoals; critical observation, identifying key information; critical action, taking decisive actions toward objectives; and self-correction, evaluating previous actions. An Oracle LLM, specifically GPT-4o, serves as the selector to identify these steps based on semantic criteria. During training, while the entire trajectory is processed, loss is computed only for the critical steps, which drastically reduces computational requirements while maintaining important context. Figure 3 provides a detailed illustration of the ATLaS implementation. On the left, we see the critical step selection process with 4 categories and their definitions. The right side demonstrates how step-level fine-tuning works, computing loss only on critical steps, highlighted, while maintaining the full trajectory context. This approach provides 2 key benefits. It dramatically reduces training costs by focusing computation where it matters most, and it improves generalization by avoiding overfitting to expert behavior in non-critical steps, allowing the agent to develop its own approach to these parts of the task. The experiment section demonstrates ATLAS's effectiveness across multiple environments. By fine-tuning on just 30% of critical steps, ATLAS outperforms models trained on complete trajectories by an average of 5%. The ablation studies provide important insights. Training on non-critical steps actually hurts performance, while 30% appears to be the optimal selection ratio. Notably, ATLaS shows strong performance not just on the tasks it was trained on, but also on completely new environments, demonstrating its ability to develop generalizable agent capabilities rather than memorizing specific expert behaviors. ATLaS demonstrates that less is better when it comes to agent tuning. By focusing only on critical steps, we can achieve better performance with lower training costs. This approach mitigates expert bias and improves generalization to new environments. A notable limitation is the dependency on powerful closed-source models for critical step selection. Future work could explore combining semantic selection with additional metrics to further enhance the identification of truly critical steps, potentially reducing the number of necessary training steps even further, while maintaining or improving performance.